Buenas tardes. How's everybody? Our generators just went off, so that's good news. We're running on the power. Let me know your situation. So I'm going to start today talking about the calculator and how to get the descriptive statistics from your calculator. And then, as I explained, most of the notes are covered in the videos that are already on YouTube. I don't expect that you watch them all already. What I will do in terms of the test is I will give you the test tomorrow, and then you can submit it by Sunday, just in case you need more time. Buenas. Okay, so I will open it up in YouTube, and then you can enter and exit the test. I think I'll set it up with unlimited attempts, but it will not grade your work until after the time has expired. And then you'll see your grade. So what you can do is, after you've sent the test, you can send me any of your handwritten work that I explained would be used to justify or give you part marks in the case that there's some misinterpretation of a problem, or oops, I lost connection. Uh-oh. I have to reconnect my iPad, but I'm here. It's power saving. So where I'm going to go, I'd like to go to the sample problems document. And discuss this one. So this is a nice exercise. Here we're going to compare two baseball players. We're going to make, we're going to approach this question in a systematic way. Who is the better baseball player? Who's the better hitter? We have two famous baseball players, Roger Maris, who had a career from the 60s to almost the 80s. And we have Babe Ruth, who had his career in the 30s and 40s. So Babe Ruth held the record as the greatest baseball hitter of all time because he had 60 home run hits in a season. But when Roger Maris came along in his shorter career, he had one season where he had 61 home run hits. So in terms of the statistics, the baseball statistics, Roger Maris superseded Babe Ruth as the best all-time hitter. And since then, somebody else, and I'm sorry, I'm not a baseball aficionado or fan, so I don't know who it is, but for some time, Maris held that record. So the question is, despite that, could you make an argument that Babe Ruth is the better baseball player? Based on his 15-year career, home runs, hits in the season, is he a better baseball player? What do you say by just looking at the numbers? How do you comment? Without making any calculations, just looking at the data. Okay, so Nivette says she thinks that Babe Ruth is a better hitter because his numbers are above 40. The majority of his data is above 40. And 40, she's using the number 40, I guess, arbitrarily because most of them are in the 40s or 50s. So let's see in a systematic way. Let's use the 5 features and make the argument. Because I tend to agree with her. His hits are higher, and the total number of hits in a season are higher, and consistently so. Right, Valeria. So we got to make our argument in a systematic way. And it's kind of obvious, anybody could say that, but it's really important to use a simple example where you know the answer to devise a methodology for making your argument, right? So a framework. So this is what we're going to do. The way we're going to look at the data is we are going to, actually, let me get the data from here. That again. So actually, I'm going to put them, I'm going to put this one over here and this one over here. There's a reason for this. So what I'm going to do is make what's called a back-to-back stem and leaf plot. And we learned how to make a stem and leaf plot. Since the highest number is 61, then the digits have to be 2 digits, right? But what we're going to do is have them share the stem. Now, in the spending data, we did classes of we use classes of 5, 0 to 04, right? 05 to 09, 10 to 14. That's what we did. Right, so he's more consistent. There's a difference in the lapse of career, yet amazingly Ruth is still the better player, so yeah. With progress, still Ruth is outstanding next to Maris. And then a longer career, yeah. Yeah, there's many reasons to argue. But we're going to use the 5 features of the distribution to make our argument. So what I'm going to do is make a back-to-back stem and leaf plot. And let's try and just go by tens. Let's see what that looks like. Now in the stem and leaf for the spending data, in the stem and leaf for the spending data, we went by 5s, like I said. I have a discussion in the notes about why I go by 5, why didn't I go by 10? Now the decision for me to go this way was because it suited my concluding discussion about 3 classes or 3 groups of shoppers, whether it's high, middle, and low income shoppers, or that these are different types of shoppers. Whatever the case, we'll leave that to further investigation, but going by 5s allowed me to see 3, and I believe 3 is meaningful. I believe that if I had more data, it would still show 3 mounds or 3 peaks of data. If I was to go by 10, you'll see that you'll lose this group. These will be combined together, and it'll only show one big group and then a skew to the right. So I chose to go by 5s instead of 10s in this case. In my argument for the baseball players, I'll be able to make my argument just going by 10. The thing is, you might ask yourself, how do I know which way to go? She doesn't have a consistent method for doing this. You'll have to try to draw it a variety of ways. Go by 5, go by 10, even go by 2, and see which one you prefer, okay? If you're working on this yourself, as long as you're consistent with your description and statistics and words and your graph, as long as they're consistent, it's correct. All right? It'll be considered correct. You just say, leave it to future research, unless it's, unless I tell you exactly what to do, you follow my direction. You can do that. Draw it different ways and see which one you can defend. So I'm going to put Maris on this one, this side. This is the stem, that they share, and then this will be the leaf. And for Maris, oh, I have to put the numbers in order, so let's do that. Trying to clean things up a bit. So I need to put these in order. That's the first step. So putting these in order then, the first number for Maris is 8. The next number for Maris is 13. So then, you know, sometimes the data comes in order, like in the spending data, and sometimes it doesn't. 16. And there's just a few, so it's not so tedious. It'll be done quickly. 23, 26, 33, 39, and 61. And Ruth's first number is so much higher than Maris. Ruth's first number is 22. 25, let me know if I make a mistake. 34, 35, 41, 41, 46, 46, 47, 46, 46, 47. Oh, and even another 46. $47, 49, 54, 54, 59, and 60. Okay, so I put them all in order. Okay. Now, we're going to put, we're going to put Maris's data down first. So Maris is, the first one is 08. Put a digit in front. We have to use 2 digits because most of the numbers are 2 digits. The last one has 2 digits, so they all have to have the same 2 digits. So it's going to be 0 and 8. That'll be the first one. And then 13, and then 14, and then 16. And then I go to the next one because it's a 23, 26. Then the next one, 33, 39, and all the way over here, 61. And that's it. Now the stem shall be shared with Ruth on this side. So Ruth's leaf, you know, a leaf is like a plant, right? The plant leaf. Okay. The stem that holds it and the leaf. All right, so 0 is not, there's nothing there. 1, nothing there. The data begins at 22. It's 22, 25, 34, 35, 41, 41, 46, 46, 47, 49. So that's obviously the most popular group. Remembering now how I think it was Nivette mentioned about the 40s. And then 54, 54, 59, and 60. So what do we see? Now we see this back-to-back stem and leaf plot shows, well, it gives us a way to compare the two distributions very neatly. The next step is to smooth this out. So I'm going to smooth out Ruth like that, and I'm going to smooth out Maris like that. Oops, went too far. I'm going to smooth Maris like that. So what do we see? How do we conclude on both sides? 1 and 1. Shape. Ruth has a symmetric distribution. Most of the values are in the center. Some are lower, and just as many, even though there's 3, are higher. The way that I've drawn it, I've said, I believe if I had more data, this would just fill in here and have this shape. Maris, it's not symmetric. We would call this right skewed, because if you put this on its horizontal axis from small to big, we see the tail is high numbers, right? There's high numbers in the tail. So this will be considered right skewed. Did I miss a number? Did I miss a 28? Where's 28? I missed a number? 8, 13, 14, 16, 23, 26. Oh, I guess I did miss a number between 28. Okay, let's put the 28 down. So where does that go? It'll just go here. Thank you. Right. So this is right skewed. Just a few high values. With high values, sorry, on the right side of a number line, that's where you find the high value. So that's called right skewed. So based on the shape of Maris, the center would be calculated as the median because it's right skewed. To calculate the median, we use n+1/2 observation, which would be what? Well, Maris has an n of 10 and Ruth has an n of 15. So this would be 11/2. This would be the 5.5th observation, or the average of 5 and 6th observation. So that's 23 plus 26 divided by 2. So remember, for right skewed data, we don't use the average, we use the median, or for skewed data. So what do you get? So it's 24.5 hits, right? So that's about 25 hits. 25 home run hits. This is my symbol for approximately. All right, so what about for Ruth? Since it's symmetric, the center is actually the mean. So I want to show you with the calculator how we'll enter these values into the calculator, okay? And I'm going to use the TI-BA2 Plus. Maybe you learned yours. You can let me know which one you have. But you should compute using your calculator in statistical mode. So let me show you how to do that on the TI-BA2 Plus. Very good, Gabrielle. So to put this in my calculator, I hit second data and I start entering numbers. So I'm going to enter the original numbers. 54, enter, and you use the arrow going down. It asks for Y because this calculator does 2 variable statistics, but I don't have another variable. I just have one variable, and I use the symbol X for that. Very good, Gabriel. So then let's keep going. Just scroll down again. And then enter 59, enter, down. 35, enter, down. Oops, no, that wasn't supposed to be. That's just a 1, enter, down. So then for the third value, $35, enter, down, down. And then 41, enter, down, down. 46, enter, down, down. 25, enter, down, down. 47, enter, down, down. 60, enter, down, down. 54, enter, down, down. 46, enter, down, down. 49, wow, it's more than 49, 46 again. 41, 34, and 22. Let's see if I made a mistake. So I'm going to look at the values again. So 54, 59, 35. So this is why we like stat mode, because we can review our numbers. 41, 46, 25, 47, 60, 54, 46, 49, 46, 34, 41, sorry, 34, and 22. I thought maybe you missed that. So to start, you hit second and data. Second and data. That's for this calculator. For other calculators, you might just be able to go right away and start entering with your M+ key. Depends on the calculator you have. In the TI-84, you can make a list of data like you would in Excel. I can also show you in Excel if you'd like. Let me know. Is that okay, Valeria? So once you hit second data, you start entering. Tell me when you're done entering. Let me know when you're ready. Okay, I can show in Excel. Just let's finish this and then I'll show. Very good, Nivette. Okay, we'll go through the results. Oh, I lost my connection again. If I don't touch my iPad, it turns off. I need to change that. Okay. Ready? So to see the results, we hit now second stat. Very good. You hit second stat. Yes, you put all the Y's as 1. I don't know why it's not showing you my iPad. I have to get the connection again. I'm connected. I don't know why. Oh, maybe it's there and there it is, okay. So we hit second stat, and we get this. What does LIN stand for? What does LIN stand for? Right, LIN stands for linear, okay, because it assumes that you are doing two variable statistics where you're checking for a linear relationship, but we are not. We're just doing one, but that's what comes up. It says linear. So now we continue through the results. N was 15, that's the sample size. Here is the mean. This is the sample mean, X bar. The answer is 49.3 or approximately 44 hits. This is the sample standard deviation, 11.25. Okay. And I made a video about the sample standard deviation. You need to watch it, okay? And then this, what is this? What's the difference between this and this? Well, the sample standard deviation is higher than this thing. Does anybody know, did you see the video about this? What's the difference between these two? Which one do I use? This is the sample standard deviation, and this one is behaving as though you have the population data. The calculator doesn't know which is, what it is that your data source is. So if your data is a sample, that's the sample standard deviation. If your data is from a population, this is your population standard deviation. Right. And what's the difference in the calculation? I'll show you in a second. Then this would be for the other variable, but we don't have another variable. So let's talk about that briefly. So we have our results that the mean is the sample mean x bar, which was 43, what was it? 43 point, gotta go back. 43.93, okay. So 43.9. Or I'll say 44 hits, okay? I'm comfortable rounding it. And then for the measure of spread, I already calculated. For a symmetric distribution, we have to use the standard deviation. Again, we have to use the mean, or we use the mean because the mean is the expected value when the data is symmetric. When the data are symmetric, notice the mean, the modal class, and the median are all in the same place. They'll all be in here. But the convention in statistics is to use the average. Statistical software will calculate all of them, but our tendency is just to use the mean, okay? They should be all in here, or there should be similar values anyway. The standard deviation is a calculation of the, I should put it on another page. So where the mean is the average, the standard deviation is a measure of how spread out the data are around the average, because the values are all spread out evenly on both sides. Some values are higher, just as many values are lower. Some values are much higher, just as many values are much lower. And like I said, I smooth it out to say that if I had more data, I think this all would fill in and be very balanced. Okay? So because of this symmetry around the center, it's like a mirror on either side, I can talk about, what did I just do? I can talk about the values being spread out around the mean. So the standard deviation is a calculation of the average it's like a measure of the average of the deviations, and we have to use the squared deviations, and that video that I made explains why, from the mean. The formula looks like this. So this is the deviation from the mean. This is how far each value, I'm going to go through all of the values. This says go through each value and subtract it from the average. And then you have to square it. The reason you have to square it, it turns out that because the values are centered around the mean is the balancing point. Just as many values in distance and magnitude are on the left as there are on the right. Okay, so whether it's skewed or symmetric, that's going to be the case. So if you try to average the deviations from the mean, once you sum all these deviations, the deviation is 0. Now watch that video about the standard deviation to follow and understand that, but the sum of all these deviations is 0 because the mean is closest to all the values on each side. So it's in a balanced way. When you get the deviations, the ones above will be perfectly offset by the ones below. And when you try and sum those deviations, some will be positive, some will be negative, and they're going to make 0. So to avoid that, all you want to do is you want to get rid of the sign. To eliminate the sign, and maintain the magnitude, like the value. We don't care about the sign. That's why we square it. But then at the end, when we're done, we have to take the square root. So this is the average of these square deviations from the mean. And an average, like this is the sum function, it means add them up, and this means divide by n minus 1. When you see those values together, like usually an average has an n on the bottom, but this is basically the same thing. I call it the average. Anytime you see that, you call it an average. And in fact, statistics is about averages and relative measures. It's just a bunch of averages that we end up talking about. So I have to put this on here. Okay, so the standard deviation is the square root of the average of the square deviations from the mean. This thing is called the variance. I'm doing a really fast summary, but you can watch all this in the videos. So this in here is called the variance. When you take the square root, you get what's called the standard deviation. Now, the n minus 1, if n is large, so let's say n was 1,000, then this would be 999, and it's not going to change your number much if you're dividing by 1,000 or 999, right? So for smaller distributions, this might have more of an impact, or smaller data sets, it might have more of an impact, but the importance of it is that it's adjusting for bias. Remember that S will be bigger than sigma, always. Why? What's sigma? The population standard deviation looks like this. It's also the square root of the square deviations from the mean, but it's an average with all the population values. And the mean is not the sample mean, but it's the population mean. I actually have to, if I have the population data, I can calculate the population mean, and then I can get the population standard deviation. So it's really because of this. Because this estimate has an estimate inside of it, what we have to do to ensure that we are not biasing our measure of standard deviation, we allow it to be a little bit bigger because we want the spread, the measure of how spread out the data is, to be able to capture the actual spread of the data. So this one value that we use in here, this other estimate inside an estimate, what it actually does is x bar is calculated how? It's all of the values of x from the data sample divided by n. So it ties all of those x's together. By tying all those x's together, where each x I say the x's, but the observation each observation contributes what's called a degree of freedom, a degree of randomness. But when we tie those observations together, we lose a degree of randomness. And for that reason, we adjust our sample size to be one less. And what this effectively does is let S be a little bit bigger than if we were calculating the population standard deviation, making it able or capable to capture the spread of all the data. And now I'll demonstrate how we use S and sigma in a moment. All right, so this is the long, well, I guess it's kind of long. It's kind of short explanation, kind of long. I have to take the square root at the end because I squared all the values here. And when you square all the values, you also square the units to get things back to the original unit. So in our case, we're looking at hits, right? Once we start squaring values, we are talking about hits squared, which makes absolutely no sense. So even though we squared the values so we could get rid of the sign and get a sense of the deviations from the mean for our average, we have to take the square root to return our values to hits, the actual variable units. So that's all I'm going to say about standard deviation. Watch the video that I already made, the pre-edited one, for the full description and step-by-step calculation, so to help you understand where this comes from. It essentially comes from here, but still understanding the nature of it. So what we got in the end was, what we got from our calculator is that S is equal to, I'm not going to remember, I got to go back. S was equal to 11.2. So we'll just say, we'll round it up to 11. So we'll say 11.2. So in my notes, I explained to you that to get the answers that I get, you need to report two more decimal points than the original data, and I pretty much stick to that rule. So because I had no decimal points in this data, I should keep 2, but I keep on using 1. But anyway, I'll just leave it. I'll put 2 just to be consistent. Let's see, what was that? So this one's 11.25, and this one was 43.93. Okay, so let's do that. It doesn't change anything, just to stick with my rule. So 2, 5, I said. Is that what I said? 2, 5. Okay. So that still rounds to 11 hits if I want to round it. So what do I do with that? That's not good. I can't seem to get that one to go with it. All right, so now what I want to do is talk about how we interpret the mean and standard deviation. The way that we use it, because of the symmetry, we can take the mean and standard deviation and create intervals This one is 1 standard deviation, an interval of 1 standard deviation from the mean. What would that give us? So this would give 44 minus 11, comma, 44 plus 11. That's not a bad calculation. So this would give 33 to 55. So within 1 standard deviation, how many observations do you get? From 33 to 55. So let's see. From 33 to 55, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 observations. What percentage is 10 out of 15? So that's 67%. So we can say the majority of observations are within 1 standard deviation from the mean, and that is usually the case, okay? That will usually be the case. It's known as Chebyshev's theorem, which I'm not going to get into for this course, but basically that should always be the case. Within 1 standard deviation of the mean, you should find the majority of the observations. Did I make any mistakes here? Does that work? Does that work for everybody? Yeah, the rule for the test should be to get 2 more decimal places than the original numbers is just a good rule for scientific notation. Anyway, it works to get the right answers. So anyway, let's look at 2 standard deviations. So that's 44 minus 22. These numbers are easy to deal with. And this is 44 plus 22. So how does that simplify? That ends up being 22 and 66. So 22 to 66 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's all the numbers, isn't it? Except for, it's all the numbers. 22. It's everything. So this is 100%. So within 2 standard deviations, you have 100% of your data. That denotes a very tight distribution. It's very tight. It's not spread out. There are no outliers. outliers would be outside since everything is inside 2 standard deviations, there's nothing outside of 3. So there are no outliers. So there's no gaps and no outliers. That will be the fourth feature. And it's a single peak. So we've really finished Maris. Ruth. That was very easy for Ruth. Now we have to finish Maris analysis. Any questions so far about what I've done? Okay. Are you learning something here? This should be not difficult. It should be clarifying. If it's very difficult what I'm saying, let me know so I can slow down or clarify better. So let's wrap up for Ruth. I made a stray line here. I gotta erase it. Oh no, that's 1. That's not a straight line. So funny. Okay. All right, so let's wrap it up. The next feature is for gaps and outliers. None of either of them. No gaps and no outliers. And 5, peak. There's one major peak. Between 40 and 49. And that's it. So this reflects Ruth's predictability, the consistency with an average of 44 hits, right? This makes him the better baseball player. This means consistency. There are no curiosities, nothing surprising, no gaps or outliers. No irregularity. Okay? Oh, the 2S is 2 standard deviations. We calculated standard deviations here. So 2S means 2 times 11, so 22. So it's 44 minus 22, 44 plus 22. Is that better? And what I concluded was that it's a very tight distribution. All the data is within 2 standard deviations, where we define outside of 3 standard deviations, you would find outliers. We're not even close to that. All the data is together. We have none. Yes, you do that to see if there's an outlier, or you just do it to see how spread out the data is. That's how you use, this is the way you use mean and standard deviation. This is your best use of it, to make intervals, to interpret what you have. So a high standard deviation means very spread out. A small standard deviation means tight distribution, more consistent. Okay. All right, we're going to jump to Maris now. So where did we leave off? So Maris, the center was the median, and the spread, we have to do the range and the 5-number summary. Range is equal to the max minus the min, which would be 61 minus a minimum of 8. What would you get? $53. And then we need the 5-number summary. Which is the minimum, Q1, Q2, Q3, and max. The minimum is 8. The minimum is 8. The median we solved as 24.5. I've got to put the full number in there. 24.5. The rounding that I did was just to make it, because they're hits, right? But when we make statistical calculation, we should use the original numbers. I guess here I didn't have to round, but this was just a quick look at the data. In general, you should keep the decimal places 2 more than the original numbers. All right, so up to 2 more. We've had a good stream so far. Had a good hour. All right, so then we need to find the other one. So it was 24.5, but that's not a data point. It's between 2 of them. So we're going to divide the data in half between 23 and 26. So the data is divided here between 23 and 26. So what I want to do is find the middle of these observations. How many are there? Well, there were 10 divided by 2, so there's 5 in each. So if there's 5, the center is at 3, right? 5 plus 1 over 2 is 6 over 2, or 3. So this is where you'll find the middle of the first half. So 1, 2, 3. This will be the middle of the first half. And 1, 2, 3. This will be the middle of the second half. Are you guys following me? So 14 will be the first quartile, and 33 will be the second quartile, a third quartile, and then we end with the maximum. Now in the notes and in the videos, I do more of a discussion about analyzing that distribution. It's clearly right skewed. We can see that But you would also be able to see that in a box plot made from this 5-number summary. Any questions about the 5-number summary? We could also calculate the IQR. Remember, the IQR is the Q3 minus Q1. So it's how spread out the middle 50% are. The more spread out, the more variable it is, the more curious it is. So we're going to have to do this now where we figure out if 61 is an outlier. Q3 is 33 minus 14, which gives us 19. So what's the next step? Number 4, gaps and outliers. Big gap. From 40s and 50s, there's no data. Okay, so this clearly separates this away from the greater portion of data. This is sitting apart. We need to check if it's a statistical outlier. So yes, there's a gap. Or I'm going to put gaps. And then verify if 61 is a statistical outlier. How do we verify that? Okay, you guys, good that we're talking about this. Okay, so how we check for outliers. When the data are skewed, we don't check like the way we did for the, we don't check the same way that we did for the, sorry, I'm distracted. We don't check the same way that we did for the symmetric distribution. We check the way we did yesterday. So when data are skewed, on the right, we have to check if there's data outside of Q3 plus 1.5 times IQR. So what we do is we take the 19 we multiply it by 1.5 and we add it to 33. So remember what we did yesterday. And look what you get. What do you get? Very good. Very good. So this one's 61.5. So it means there are no values higher so actually, as much as 61 looks obscene, it's just on the border, just before the threshold for outliers. So there's no statistical outliers. It is an outlier in a loose sense, that it's away from the data, there's a gap and all of that. But in statistical terms, it's not technically an outlier. Now, we can talk about it being a weird number, and we could even investigate that maybe Roger Maris, has very unusual. This is a very unusual number when most of the data was below it, far below it. So that would require some sort of investigation to see if maybe he was using some performance enhancing therapy and, improving his performance, even illegally, because you're not allowed to do that at the time, and I don't even think you're allowed to do it today. So, but anyway, technically speaking, it's not an outlier in statistical terms, but still worth investigation nonetheless. Okay, so 5 is peaks, and my response to the question about peaks in this case is that there really are no peaks. The data just kind of is flat. I'm going to call it no peaks. This is no peaks. There's no real determinate place. If you were to bet on Roger Maris's season hits, where would you go? There's no real place to feel confident. It depends what kind of, how you can guess. If you had to guess an exact number, look how spread out this is. You wouldn't know where to start. Nothing in here, so you probably wouldn't go for that. This looks like a long shot. So would you go in the middle of this data, or, it's hard to say. So I wouldn't even call this a peak. It's pretty flat. So my comment when I talk about peaks is that no peaks, very flat distribution, unpredictable. You could also say unreliable or volatile. These are just some of the terms. I wouldn't bet on him. So I would conclude arguing that Babe Ruth is consistently a higher hitter. His average hits is almost double of Maris's. with 44 home run hits average. Maris was, what was the median? It was 24. You know, it's so much higher, and it's so much more consistently higher that all the data appears in 2 standard deviations from the mean. And Maris's is very spread out, no real peaks, non-predictable. And for this reason, I would say that Babe Ruth is the higher hitter, even though Maris had a 1 year. He's a one-hit wonder, 1 year banner season, great season. Any questions? We didn't make the box, but you could make the box if you wanted to make the box for the box plot, and that helps you visualize better. I avoid doing that without a ruler. Maybe I can put a ruler here. I know there's a ruler here, but I can't really read it. Let's see. If I put a ruler and I mark it, is that going to help? Oops. And then I mark 8 to 61. How would I do that? Okay, so let's see. So, oh, every time I touch something, I lose a ruler. So if I start here, it won't let me. Why? Like, I want to use the ruler, it won't let me do the ruler. Doing something wrong here. Okay, so that's 8, and then 9, 10, 11, 12, 34. So I'll say this is 14, 15, 16, 17, 18, 19, 20. So this is 24.5, something like that, and then 33. And then 61. Oh, no, I'm not going to get to it. It's going to be way over here. It'll be like way over here somewhere. I can waste a lot of time playing with this. Oh, that didn't work. No, it's all separate. Anyway, so if I was to draw it, and that was it, and I make the box, take off my thing, and this would be the middle of the box. So notice here, if I drew this properly, okay, so this looks inside here like it's left skewed because this side is bigger than this. But when you go outside and you look at the whiskers here to here, when you look at the whiskers from here to here, this side is much more right skewed. And that's why we would say, even though the inside is left skewed, the right side is right skewed. I mean, the outside is right skewed. So for that reason, and so much more, I need to get rid of this pencil. And it's greater in the right skew. So this ends up being a right skew distribution. That's how you use the box for looking at skew. And then we can use it, this box here, to add 1.5. So 1.5, see, the scale is terrible. This needs to be way more out to the right. But anyway, 1.5 of these will cover 61. That's the main point I want to make. I don't like to draw unless I have the right thing, and I did that in the notes. I made them to scale better, because 1.5 of these will certainly supersede the 61. All right, I'm done here. So that's what I want to say about that. I want you to watch the videos for that. And it's 7:30, so we have an hour and a half, or we have about an hour. What I want to do next is talk about more of, sorry there. Okay. So we talked about Maris and Ruth, we talked about the spending data, and then I did some background stuff, and I wanted to talk briefly about this because this gets us to the next unit. So this is Newcomb's data. So Newcomb was a scientist like 200 years ago. Was it 200 or 300? Let me see what I said here. I said it was 100 years ago. Simon Newcomb repeatedly measured the time in seconds that a light signal took to travel 7.4 kilometers from his lab to a mirror at the base of the Washington Monument. As a measure of the speed of light, he would then divide 7.4 kilometers by the approximate time it took to travel the distance. The speed of light will be measured in kilometers per nanosecond, where there are 10 to the power of 9 nanoseconds in a second. And the questions we want to answer is, what would be the best approximation of the time light takes to travel 7.4 kilometers? That should be used in the calculation. And would we come up with the same measure of the speed of light? So the data that we have is just in deviations from 24,800. It's a very precise measurement. It's very fast, speed of light. But there is some variation for variables that I'm not going to get into, but there is slight variation. Traveling it over a long distance helped to realize, that those numbers and that slight variation. So this is the data that is put into a stem and leaf plot for Newcomb's data. And what you see is most of the data is in the 20s. Okay? This is really the greatest peak, the only peak. The center of the only peak. But then there's some observations over here that are far away. In fact, it turns out that these are outliers if you test them. So when you see outliers, you need to get into, even in the Maris in Maris's home run hit season data, I suggested, even though it wasn't a statistical outlier, it was worthy of investigation. Outliers are values set apart from the rest of the data, should be investigated. Now let's see, what could be the nature of this? Is it just a natural phenomenon, or is something else going on? And the way that this was examined is, rather than just look at the data grouped in common values, we looked at the data, we can look at the data in a time plot. So this shows the order that the measures were taken. So the first measures were up here, second, third, fourth, fifth, sixth, 7, 8. Oh, I missed that one down there. Whatever. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you get the idea. So what you see is that these values occurred early on, but never again. So could it be that these were the result of something else, not to do with the phenomena of the speed of light? Could it be that early on the research that was being conducted and or the calibration, the whole setup for sending this light signal and the measurement on the other end, all of those elements of this trial, or this experiment really, was conducted in such a way early on that it was a matter of time before learning was done on how to do that accurately or properly. So maybe these were just mistakes. Maybe these were just what we call measurement error. Measurement error is when you actually measure the value incorrectly. Like if you use a scale, but the scale wasn't calibrated correctly, or if you use an instrument or let's say they were using I don't know what they had to measure time back then, but maybe their stopwatch, but they were just trying to get used to using it and starting it and stopping it. That measurement took time to learn how to take. So those would be measurement errors, something wrong with the actual method used in measuring. Another kind of error would be like a data entry error. That's different. That's when you're actually transcribing data from maybe some paper, that the responses are recorded somewhere, or the outcomes are recorded somewhere, values are recorded somewhere, but then when they're transcribed incorrectly. So that could be possible. And the other possibility is that you actually have some sort of paradigm shift, something in the phenomenon that needs to be noted. Like in the case of Maris, something's going on with the 61 home run hit season, that it's worth investigating, that he was doing something different. It would be interesting to know what exactly made him perform so well. So I'm going to pick, in this case, likely measurement error, something that took time to learn, and once it was learned by the research staff, you never saw those numbers again. So as a result of measurement error, unless we could correct it, which we can because it's old data, we can't retake those numbers. I mean, guess we could, but we'd have to repeat this experiment. We just throw them out. We can just throw them out, and it's not going to affect. Most of the data is within a very predictable range, around 20 to 40. So we're going to drop them. So you shouldn't be dropping outliers unless you have a good reason. Once you drop them, you see we get a nice symmetric bar graph. This graph is called a histogram, and I do have a video on histograms, but I do want to reproduce this histogram together. Some of my programming code is for Stata, and I don't expect you to do Stata, but I made some of this data. I plotted it using Stata. Oh, I never did show you guys Excel, right? Maybe I can show you Excel now, and then we'll do this. I never showed you Excel, how to do mean and standard deviation. And I haven't practiced making a histogram in Excel in a while, but you can find instructions on how to do that as well. So let's do that, and then what? Then I want to talk about weighted means and weighted standard deviations, and then we'll go. So let's see. I was going to show you Excel. So Excel. So for Excel, let's go back to Ruth's data, right? Let's look at So I'm going to enter Ruth's data in a column 22, 25, enter, return 34, no, that's not a number. Yeah, 34, 35, 41, 41, 346s, 47, 49, 54, 54, and 60. And what I want to do is average. So you say equals average, and you see you get a drop-down list of different functions. And you tell Excel that you want all these with a colon to go in. You guys can practice this later if you don't know how to do this. Is that the answer? That's not the answer. I must have typed something wrong. It was 43. So let's see, 22, 25, 34, 35, 41, 41, 46, 46, 46, 47, 49, 54, 54, and 60. So maybe I did something wrong before. 54, 59. Did I get anything wrong there? You didn't see. Let's see. That's not the average. 59 missing? Oh, great, 59 is missing. Thank you. 59.60. So equals now average, and you make, okay, so this is my iPad, so it looks a little different than what you'll use in Excel, but the functions are the same. So that's the number that we're used to seeing. Okay, so that's average, and then we want the standard deviation, and standard deviation is standard deviation like this. And you're going to do the same thing. Make a bracket, highlight, bring it down, and close the bracket. And it looks like it didn't work here. Anyway, let's see. It did work. So is that it? Was that the standard deviation? I don't think so. It was 11. What happened? So let's use I'm going to use standard deviation S because I don't know if that is something different than I'm used to seeing. Standard deviation S must be sample standard deviation. I don't know why there's all this noise around here. Like I said, this is my iPad Excel that I'm not used to. Should that work? There it is. So I don't know what the heck the other number is giving me, but this is standard deviation of the sample, or sample standard deviation. Let's write it like that. So this is the sample mean or sample average, and the sample standard deviation. Questions? So just repeat, you have to press equals and then you get to pick a function. And let me do that somewhere else. So if you said equals and then you get to pick a function, and there should be a drop down list. If you touch function or you tap it, and you see you can go between financial, logical, text, and statistics. So these are all statistic functions available to you. Quite a few. Excel has there's lots of description on how to use Excel in YouTube, and the help is pretty good. Pretty much taught myself to use Excel. Okay. Thank you for your help. So you guys can ask me to do calculations in Excel when you think you'd like to see that. All right, so we want to make this histogram together. And the way we do that is going back to the data that's listed over here. This is the data. I'll make it as big as possible. So this is the Newcomb data. So we already dealt with this data set. So this was in Excel with Maris, Ruth, spending, and now Newcomb's data. So here's Newcomb's data, and I'm going to wipe out this one and this one because these were determined to be outliers by our brilliant analysis. So the data really starts at 16 and it goes up till, what's the highest value? So look at all the 24s, 25s, 26. I think it goes to 45 or 40. Okay, so that's the highest value, 40. So, oops. So for Newcomb's data, so this is all in the sample problems document. in Newcomb stat. I'm looking for my pen. Where did I put my pen? I found it. So, what I'm going to do is I'm going to steal this. Now, people might find this tedious, but it's really important to know where a frequency and relative frequency histogram come from. Oh my goodness. Okay. So, there are now 64 observations, and the range of values is between 16 and 40. So what we're going to do in setting up the frequency. Well, Alexandra is asking for the quartiles. Okay, I should mention to you about quartiles before I continue. Statistical software will calculate quartiles in a non-standard way. I've been teaching this class for 20 years, and it seems like everybody does things differently when it comes to quartiles. And it has to do with them thinking of it as a percentile. So in the end, the conclusion is don't use statistical software for the quartiles for this class. In general, it doesn't really matter. But if you want to avoid going insane or getting the wrong answers and not knowing why, you're supposed to take 10, you have to take n, the p percentile times n to find the observation where it is. So if you were to do that for the 25th percentile, you would do 0.25 times 10 or 2.5. Now which one did we pick? Well, that's not the ordered list, so now that's confusing. Let's go to the ordered list. Oh, that's not going to be easy. I have to group everything again. Okay. So what did we do? When we did this, I put them in order and I picked this one and this one, right? So you could call that 2.5 and you could call that 2.5. It'll get you here. But some calculators or computers will call that this between here and here 2.5. So they would average this. So it results in different answers. Makes it very confusing. Oh, I lost you. I think I lost the connection. Hold on. Again. Yeah, I broke the connection. Hold on. Okay, so what I was saying is, with that calculation I just made here, the 25th percentile, and I explained it in the notes, is computed I lost connection. Let me check if I lost connection from the live stream. No, we still got a good signal. It's 8 o'clock. I've been lucky. Thank God. So the 25th percentile is found at the 0.25 times n observation. Or you would calculate 0.25 times 10 to see 2.5. Then I went to the ordered list here. Remember how we counted? So we found the third was the 25th percentile, but this is telling us to go to 2.5. So is 2.5 here, or is it between those two? That is the problem. Okay, so the way we're doing it ends up with a different answer than a computer would calculate. The computer would probably calculate that the average of these two, which would be 13.5 as opposed to 14. So that'll just throw you off. So when it comes to using Excel, you could use it for percentiles, but for this class, just don't. In real life, it's fine. Okay. Now there's probably a way to get them to be the same, but I've not looked into it too much. This got messed up. Okay. So where were we? I was making this histogram. All right. So back to the histogram. So what we do for the histogram is, this is my variable. I use the symbol X. And then I want to count the number of observations in a range that I'm going to specify. And then I want to compute the percentage of observations in a certain range. Now my first range, I'm going to go by equal intervals. And this is, you can follow instructions to do it, or you can use logic. I did give some guidelines in the notes about how to divide up into equal intervals, and depends how many intervals you want, right? But this time I'm going to start at 15 and I'm going to go till 20, but not including 20. Now this is different than what we did with the stem and leaf plot. I'm treating this as continuous data, and I'm allowing for decimals. To do that, I could have, 19.9999, and I want it to fall in this group. And the next one will have 20 in it, but this one doesn't. This one excludes, so this means exclude 20. But include 15. This one says include 20 up until 25, but exclude 25. Okay. So in this way we make our categories mutually exclusive, like separate. no overlap. So rather than putting 26, I'm going to start at 25 and go till 30. And the next one is going to include 30 where the other one didn't until 35, but not including 35. The next one will be 35 up to but not including 40. And the final one where I need 40 because 40 is my last value, I'm going to go till 45. So I have 5 intervals. Now you have to count how many observations in each of these. In Excel they call it bins. I'll call it classes again. I'll use that terminology. So how many observations fall in this class? You have to just count. And I've broken them up in groups of 5 to make it kind of easier. So you want to go up to 20, but not including 20. The first one is easy, 1, 2, 3. And the next one, 20 to 25, is a little bigger. So there's 5, 10, 11, 12, 13. All right, so I said 5, 10, 11, 12, 13. I'm good at adding by 5s. The next one includes 25 all the way to 30, so this is a big one. So I'm going to count these groups first and then add in these ones here. So it's going to be 5, 10, 15, 20, 25. Okay, what happened? Do it again. 5, 10, 15, 20, 25, 26, 27, 28. Everybody agree? And then, you ready with me? Should I slow down? To get the range of the classes, again, just like the stem and leaf plot, just try a few different ones and see what you think. But like in this case, the range is between 16 and 40, right? So, and I want 1, 2, 3, 4, 5, 6 classes. So if I want 6 classes, I can take the range divided by 6 to see approximately how many values would be in it. But it's pretty standard to use 5, 10, 15, just like stem and leaf. In the stem and leaf plot, we usually refer to a stem and leaf that goes by tens, but we call it a split stem and leaf if it goes by 5s or by 2s. When it comes to histograms, we don't have, I don't know that there's any special terminology, but what the guiding principle is make the interval range fit to how many intervals you want. Okay, you got to be guided by the number of bins or the number of intervals that you need. So if you want 6, you got to take the range divided by 6 and see what kind of range you get. Or just stick with the 5s or the 10s if you can. It's easier to look at and count up. Okay, 30 to 35, next one. So 30s to 35. So we have, well, I guess I can just count them. So there's 5 here, 6, 7, 8, 9, and then 10, 11, 12, 13. There's 13 again. And then 35 till 40, 1, 2, 3, 4, 5, 6. and then 1. And that's a total of 64. The thing is, you can, if you really don't know the interval size, just make a few different drawings. And just like the logic of the stem and leaf, you have to pick the diagram that best you can explain. That you have, that you can justify what it possibly means. Like, don't make a graph that you can't explain. That's pretty clear, right? Don't make a graph and go, wow, look at this. I have no idea what it means. So make a graph that you can describe, explain. You can make summary of it with the 5 features. Pick that one that you can do that with and tell a story around. Okay, so that gives us the number of observations. So we can make a histogram with this information. This column is for the data used in what's called a relative frequency histogram. So what is relative? Well, statistics is about average and relative measures. We're going to make a relative number of observations by computing 3 divided by the total 64. So what percentage of observations fall into the first interval? Okay. So I'm going to round that, make it simple. This is 0.05%. And then the next one, 13 divided by 64, I'm going to round it to wow, what did I just do? That's not right. It's 5%. I just realized. It's 0.05 or 5%. Sorry. Thanks, Nivette. And then this one is 20%. I'm just rushing ahead of myself. So 28 divided by 64 is 44%. And then 13 again is 20%. And then 6 divided by 64 is 9%. And then 1 divided by 64 is 2%. And those should add up to what? So this should be 100%. Good. All right. And in drawing this histogram using these as the height of the bars, you're going to have a different vertical axis on your histogram. Unbelievable how this separates all the data. I haven't figured out why it does that. If I touch the corners, I can put it together. Okay. So let's make the relative frequency histogram. Oh, sorry, the frequency histogram. Put a nice straight line with my magic line maker. And I'm going to start at the interval 15, right? So 15, 20, 25, 30, 35, 40, and 45. And the height should capture these. Now the highest one will be 25 to 30, so let's fit that in first. That will be 28. So that will be, let's roughly sketch this in. Let's say, so the highest one is 28, so I need to go up to about 30. 5, 10, 15, 20, 25, 30. And then I'm going to, so that's the biggest, so it'll fit on on here. And I'm going to name the axis. This is time, and this is number of observations. That's what it is. So it's a frequency histogram. It just shows frequencies. So now I'm going to plot 1%. So 1%, and because it's such a sketch and you really can't see for sure, not 1%, sorry, 3. I'm going to put 3 first. So this is 3. I'm going to put a number 3 here just in case anyone questions the scale of my graph. So then the next one is 13. 13 is about here, right? And then's the big 28. So 28 is just about here. And the next one is 13. Ugh. And then the next one is 6. And the next one is 1. Okay, so that is a reenactment, a recreation of the distribution that we saw. The 5 features are symmetric, where the mean is a measure of the center, the standard deviation would be a measure of the spread. It looks like a tight distribution. There are no gaps, there are no outliers, and there's a single peak between 25 and 30. That's how you would see this distribution. And the histogram, what's the difference between the histogram and the stem and leaf plot? So there's advantages and disadvantages to all the graphs. And sometimes you need to make more than one graph. Oh, I'm off the scale. Oh my goodness. I'm off there. What's the difference between the histogram and the stem and leaf? Right. You do not see the observed data in the histogram. And that's unfortunate because you don't know if in this interval here, all the values are 25. You kind of assume they're somewhere on average in between, you know, but they could be all 25s, you know. They could be all 29s. We don't get to see that. We just treat them all about like they're the same thing. So that can have advantages and disadvantages. What is the advantage of the histogram? Well, with a lot of data, so one thing is you do not see the observations. And the second is the advantage. I don't know if it's bad. That's a strong word. It's not necessarily bad, but we don't see that detail. But the good thing is it's good for lots of data. You know, we don't get this long, crazy stem and leaf plot, like really, like the one I showed you in the sample problems notes. It's just a long leaf because there's so much data. All right, so what about the relative frequency histogram? What is that going to look like? Well, looking at the values, it's going to have the same pattern, right? Because even though these are different numbers, it will have roughly the same pattern, won't it? It'll have the same 5 features. It'll have the same 5 features, it'll have the same pattern. So why do we prefer to use the relative frequency histogram over the frequency histogram? So the question is, they look the same, they have the same 5-feature, identical pattern, have the same peak, the same gaps, all of that. The reason is, very good, Valeria, it's because when we look at the chart, everything is in relative measure, and it tells us how big it is. Like, I guess you could see it visually, but it's really nice to say, you know, rather than saying 13, 13 is meaningless unless you tell people that n was 65. 64. Right? It doesn't mean anything. So we use the relative frequency histogram because you're telling people immediately that 20% of the observations are between 20 and 25, not including 25. 44% of the observations, so almost half of them, are captured in this interval, 25 to 30, not including 30. Okay, so that's really important. So I could basically draw the same thing, which let's just do it quickly. Or you know what I'm going to do is I'm going to copy it. Oh dear, dear, dear. Okay, so all I'd have to do is copy it. Everything will stay the same. I could add the word relative frequency histogram. I can change these numbers here to percents. I have to change the scale too. I would change the scale, and this would become percentage of observations. I'll just cheat and not put the scale in. It'll have the same sort of pattern. But this will be 44%. It's a higher number, so you have to just adjust the scale. This would be 5%, this would be 20%, 20%, 9%, 2%, and 5%. So it would be roughly like that. It would look essentially the same. The difference is that if I was to smooth this out, we would talk about the, oh, this is way too close. I gotta move this over. Sorry, I'm being picky now. But I have to move that over because that's not 0. Oh, let me. Anyway, so what was I saying? If I smooth out the curve, it looks symmetric, and I can talk about 100% of the observation being under that curve. And when we talk about density curves, that's what we imagine. That's what we talk about. We talk about there being a relative frequency histogram under that curve where the values sum to 100%. The number of observations total 100%, of course. Okay? So that takes us to, so what else did I want to do here? I wanted to talk to you about, I really wanted to get to NOR. I want to just say a few things about NOR maybe. Or maybe we can just leave it. So, what you need to do tonight in preparation for tomorrow is watch these. So, I have videos explaining these calculations that you need to watch. The weighted mean, this stuff here. So every time I have this, it tells you to go watch the videos. So watch the videos on the weighted mean, the weighted standard deviation, their calculation, the interpretation, these formula that look very menacing, but they're all essentially the same. So I need you to watch those. You need to watch this. This is like my most popular video. I think it went viral in Asia somewhere. I don't know. A lot of people watch this video discussing the weighted mean. And then I just have some exercises to practice. And I introduced graphs with two variables and looking at them and how you visualize them. So make sure you watch this stuff, okay? It's just a basic introduction, and for most of you, it's a review of very elementary statistics. So see what you can watch about those. I want to make a brief introduction to the NOR before we end. Yes, you should finish, Valeria, the videos in Unit 2 GDS, okay? So finish the videos in Unit 2 GDS to cover all this material. I know there's a lot, but they're very short and it's just the notes. So if you've read them, they should clarify the notes. And you can speed up my voice. You can slow it down. And you can watch them, while you write the test. You can review what you need to as you go. Yeah, I want to talk a little bit about NOR. Not too much, but I want to talk a little bit about NOR. Because it fits into the discussion I just had about the relative frequency histogram. Now NOR also has most of the videos inside, so I cover most of the videos, but I really just want to talk about this before we go. This is just the first few pages, and then all the rest there's videos for, so you can watch. So all I've done, with this course is I use this time together to summarize, answer questions for you, and there's just a few things that are missing in the videos that I leave for our discussion together. But most of the pages are covered in the videos, at least for the first 3 sections of the course. So here is an example where we have a relative frequency histogram, and I can talk about smoothing this out and saying, I believe if I had all the data, that would be the pattern that would continue to exist. It would be symmetric with one peak. Because, you know, when I say that, I'm saying that because you could have symmetric with two peaks. This is symmetric with two peaks. So I have to say one peak. So we think of a density curve as an idealized, smooth, idealized version of a relative frequency histogram. We're going to focus now for the next bit, even though we've talked about asymmetric or skewed distributions, we focus most of the course discussing symmetric distributions, okay? So from now on. So we're going to talk about this symmetric distribution in detail. And see, I have the percent observations here, and I have the continuous number line that can go from a low of negative infinity over there. This goes out. It's like a number line that goes from a negative infinity to a positive infinity. And because it's symmetric, and because I've idealized it, talking about if I had all of the data possible, I think it would look like this, then that means I'm talking about the population, and the center of the population, the central value, is this symbol mu. This is the symbol for the population mean. Mu is a Greek letter M. M for mean. And I can ask you, now that we know this is a relative frequency histogram, and I know that by this, okay, that's how I know it's a relative frequency histogram. And I can ask you, what is the area, what is in the bars to the left of the mean in the center? What is the total of these bars here? So if the whole thing under the curve is 100%, what is this? What would this be? Very good. So this is 50%. And what we write is P. So this is in statistics. This is how I write statistical notation. And I say, I use X to refer to the variable. So this might be, I use the example, the heights of women, for instance, 18 and over. And I use the symbol with the big X, and I say, I use the arrow going this way. The P, that X is less than the sample mean, or I can give it a value, which I will do in the notes. I end up calling this 64 just to put a number on it. So say that's 64. So less than 64 is equal to 0.5 or 50%. The P stands for proportion or percentage of observations. Proportion of observation. It could also stand for frequency or relative frequency of observations. These are all the different terms to say the same thing. And then the other word that, because I'm looking at this as though it's the population, I can also talk about this being the chance or probability. Of seeing an observation less than 64. So this says, what is the proportion of observations under the curve that are less than 64? So when you see this, say under the curve. So with that, if I marked this here and I said this was 50, how would we write that if I told you that this was 10%? No, that's too small. I'll call it, maybe it's not, I'll just call it 10%. That's messy. So you would write the P, that the area under the curve is less than 50, is equal to 0.1 or 10%. Now, what if I wanted to talk about here to here? How much is in between here? How much is between 50 and 64? Right, not, yeah, in probabilities. So between here and here, if it's 50 all the way over and this is 10, then between here and here is 40%. How would we write that down? I could write the P, and then what I do is I put X in the middle and I use these arrows to say between the smaller number of 50 and the bigger number of 64, that is equal to 40%. Okay, so we know how to write the area to the left of a value. We know how to write between. And what if we want to go here? What if I write here, if this is 5%? And I'll give this number, I'll call it 85. So the proportion or percentage or probability that a value of X is greater than 85 is equal to 5%. So I've shown you how to write the symbols to the left, in between, and to the right. And there's one more thing I want to say before I let you go. What do we call 64? What are the different names for what 64 is? So that 64 is the mean. But I mentioned to you in a symmetric distribution, a perfectly symmetric distribution, it's also the median. Yeah, I gave you these numbers. I made them up. Well, this one's known because it's in the middle. But yeah, I gave you those numbers. You can't really see it from the graph. Right, so this is the population mean. But it's also the population median. And what's the other name for the median? It's also called the 50th percentile. A percentile is defined as the observation that has 50% of the observations below it. Isn't that exactly what it is? 50% of the observations are below it. They're all here. That's what this means. Whenever you use a left symbol like this, the 64, the value here is called a percentile. It's not exactly the mode, but it's in the modal class. Because we don't see the data, so I can't say it's the mode, but it's the modal class. Okay? So it's Q2. It's also Q2. Second quartile. So what I'm said is 64 is the 50th percentile. What do we call 50 here? What would 50 be called? What do we call 50? Very good. So this is called, so since 10% of the observations are below it, 50 is known as the tenth percentile. And what do we call 85? Very good. So 85 has how many below it? If it's 5% above, then it's 95% below, right? So 85 is the 95th percentile. Or you can call it the top 5th percentile. Okay, so that's all I wanted to say about this. We're going to pick up here when we meet again on Monday, but in the meantime, I will make the test up to here, so it won't have normal stuff in it, but I'm going to zoom through the normal distribution material. So what I need you to do is read ahead and watch the videos for normal if you have time after your test on Sunday. So as I explained, and I put in the chat, for the test on the weekend, I will administer it 9 a.m. on Saturday to 3 p.m. on Sunday. Okay? You're going to have to submit it to me on Sunday. We'll submit it online because it will be a multiple choice test online, but then also you can send your supporting documents. You have to send them both before 3 p.m. Well, I'll give you like 5 minutes to send it. Maybe 15, okay? But the test will close at 3 p.m. on Sunday. Any questions? Can you read that? So we're going to pick up here on Monday. I'm going to finish the normal distribution on Monday. On Tuesday, I'm going to do, well, let me write it properly here. I don't even know if you can see that. Let me do this. Let me do it on the next thing. So Monday next week, we will cover Unit 2 NOR. And you have all those videos to watch. So I'm just going to do like a summary overview of everything. And you can watch the videos to go step by step. On Tuesday, I'm going to cover Unit 3, regression. And on Wednesday, I'm going to start Unit 4, probability. That's my goal. And then we will have Thursday, because this is a long unit, also for Unit 4, probability. And then maybe we can have Friday for some review questions. That's my goal. So then the next week, we're going to focus on Unit 5, which has 2 parts, and Unit 6. There's no video for what I just discussed. You just got to watch this one again. Okay, Valeria? This page, I don't have a video for, I don't think, but the rest I do. What is it about the 95th percentile? Oh, because, okay, why is it the 95th, right? Because it's 5% on this side, so it has to be 95 on that side. And percentile is defined by the area to the left. So at 85, 5% is above and 95% is below. Okay, very good. So have a good night. Have good luck on the test. Let me know if you have any questions. Thank you. You guys are a great class, and you're very it seems that you have some knowledge or you're studying or something, because this is going smoothly. So if you need to slow me down, please try to let me know, either by texting me or by emailing me what I should review more intently. But for tomorrow, you're going to have time to review your notes and go to the areas that you need help on. Most of the videos are there, like I said, and the only thing I really think you need to do is watch these last videos on weighted mean, weighted standard deviation, and then this one on scatter plots. That covers just basics about regression. Before we do regression, it's just an overview of how to look at two variables at a time and the correlation coefficient without making calculations, just observations. All right, so take care, good night, have a rest if you can. Have a good rest and a good day tomorrow or weekend.